Welcome to the AWS Nonprofit Office Hours. My name is Alex Vidalucci. I'm a technical program manager with the AWS Nonprofit Program. Here with me, I have Locktrin. So Lock, please introduce yourself and take it away.
Hi, everybody. Thank you for having me here today. My name is Locktrin, and I am a senior solutions architect at AWS, and I specialize in databases. When we talk about databases at AWS, we kind of have to talk about Amazon Aurora. Amazon Aurora is part of our relational database service, or RDS family. As some of you may be aware, after over a decade of building and running Amazon.com, the company realized that it had developed a core competency in operating massive scale technology infrastructure. And one of those lessons learned is that running databases at scale is not easy. So that led to the birth of Amazon RDS in 2009. In fact, we celebrated the 10-year anniversary of RDS just last year. RDS makes it easy to set up, operate, and scale relational databases with a choice of popular database engines. And today, I want to highlight one of those database engines in Amazon Aurora. Amazon Aurora provides drop-in compatibility with MySQL and PostgreSQL with the performance and availability of commercial-grade database engines. Now, what do I mean by drop-in compatibility? What I mean is that if you have existing applications and tools developed to work with MySQL or Postgres, you can run them on Aurora without requiring any modifications. You still get the security, the ease of use, and the scalability of RDS. And then with Aurora, we've developed a cloud-native engine from the ground up that can deliver 5 times the throughput of standard MySQL and 3 times that of Postgres. And I'll dive into how we achieved that. Let's start by taking a simplistic and admittedly an overly simplistic view of your relational database engine. At the top, we have the SQL layer. This does all of your SQL parsing, translating your query into planning and execution. Then the transaction layer. This layer takes care of the processes necessary to ensure atomicity, consistency, isolation, and durability. Then we have caching, keeping frequently used data hot to reduce I/O and improve performance. And lastly, the storage layer, where the data finally resides in its persistent state. But the way that this has been approached historically is that you took all of these layers of processing and you shoved it into one box. And so you just had multiple layers of processing all in a single engine. But here's where Aurora differentiates itself from standard open source engines. Amazon Aurora decouples the compute from storage, and this allows us to provision, distribute, scale, fail, and heal all of these components independently of one another. So what does this scaled out distributed storage architecture look like? As I mentioned earlier, this is a cloud-native engine developed from the ground up. So the storage system is purpose-built for database log structures. This allows us to stripe storage across hundreds of nodes distributed across multiple availability zones. And as you can see from the illustration in the lower right-hand side, we maintain 6 copies of the data distributed across multiple availability zones. And this offers protection against the unlikely loss of up to 2 AZs plus 1 storage node simultaneously. That is, you can lose 2 AZs plus 1 and still have your data. And finally, this allows us to automatically grow storage as needed. So you don't have to guess and pre-provision how much storage you need. You pay for as much storage as you use, and we automatically scale up for you as you need it, up to 64 terabytes. And here we're looking at just a list of some of the things we've been able to achieve by decoupling and pushing storage down to its own distributed layer. We push the redo processing down to the storage layer. This enables instant crash recovery since the storage is shared and separated from the compute layer. The storage is fault tolerant, and Aurora maintains 6 copies of the data, and the storage nodes have a peer-to-peer gossiping mechanism so that if one node fails, we automatically replace it and restore data to the new node. And there are a host of features that I'll talk through in more detail, including fast cloning, backtracking, continuous backups, and point-in-time recovery, auto-scaling, and low-latency replication across multiple AZs as well as multiple regions. So let's look at some of the features that Amazon Aurora offers. In addition to being able to scale storage as needed independently of compute, we can also scale compute independently of storage. And Aurora supports up to 15 read replicas per cluster. So you can scale up to support high read throughput. And Aurora also supports auto-scaling. And with auto-scaling, you define the metric, threshold, max, and min capacity. And Aurora would dynamically adjust the number of replicas for you for your cluster to handle increases in workload. Each of these replicas is also promotable to be the primary instance to serve read and write throughputs. So in the case that you experience degradation in your primary instance, you can fail over to any of your replicas and the failover process from start to finish is typically under 30 seconds. Then beyond the 15 replicas, we can also scale across regions with Aurora Global Database. Aurora Global Database is a feature in Aurora that uses dedicated replication infrastructure and allows you to replicate data across regions. With Global Database, you can add up to 5 secondary regions, and within each region, you can have up to 16 read replicas. This gives you improved data locality and allows you to scale your data globally and bring your data close to where your users need them. Replication time across regions is typically under 1 second, and each secondary region can also be promoted to be a primary region capable of serving read and write workloads. So in the unlikely event of a full region degradation, you can fail over to a secondary region, and failover time across regions, start to finish, is typically under 1 minute. Here's a simplified look at the plumbing of Global Database. In the center, we have our primary region showing a primary instance and 2 replica instances. And the distributed storage layer. With Aurora Global Database, we use dedicated replication infrastructure to perform physical replication to secondary regions. In this diagram, we are showing 3 secondary regions. Each secondary region has dedicated inbound infrastructure to apply updates to the cluster in each of these regions. This dedicated replication infrastructure is what allows us to replicate data across regions with less than 1 second lag, and it offloads the processing from the cluster, so it has minimal impact on your database. We have synthetic benchmark tests that show consistently high performance up to 200,000 writes per second throughput. With up to 5 secondary regions, you can scale your read throughput, and in the event of degradation in your primary region, failover time to your secondary region is typically under 1 minute. We also now support in-place conversion, so if you are using Aurora today and want to take advantage of global database features, you can convert your existing cluster today without the need to create a new cluster. Aurora's distributed storage architecture also allows fast database cloning. This feature is useful for when you want to bring up a database with a point-in-time snapshot, and this could be used to run data analysis without impacting your production system, or to bring your production database into a lower environment, such as a dev or test environment. With Aurora fast database cloning, all we need to do is bring up the new cluster instance. We don't copy the data. We use a copy on write protocol. That means that we only create a new copy of the data when the data changes either at the source or the target. And this is achieved, again, because of the decoupled distributed storage architecture. Aurora also supports a serverless deployment. This was launched for MySQL in 2018 and followed up in 2019 with support for Postgres. This feature is great for infrequently used workloads or cyclical workloads, such as a dev environment that gets used during the day, and then it can shut down in the evenings when developers go home. With serverless, your applications interact with a request router endpoint, and we maintain a warm pool of instances so that when resources are needed, we automatically scale your cluster up, and you only pay for the compute resources you use when you use it by the second. And when it's not in use, Aurora can automatically shut down the instances, and you only pay for storage during that time. Here, I also want to visit one of our newer features in Aurora, announced at reInvent last year. This is the ability to use machine learning capabilities right from your database. We know that machine learning can be useful to gain insight from your data, and as it so happens, most of your data is stored in databases. But in general, in order to use machine learning, you typically need to build custom applications or processes to read or extract the data from your databases. And then you can apply your ML model. But now Aurora is natively integrated into 2 AWS ML services, Amazon SageMaker and Amazon Comprehend. You can now take advantage of this ML integration using familiar SQL syntax delivered with the performance, the scale, and the security of Amazon Aurora. For a simple example of how that works, here is a user feedback table in an Aurora database. The application issues a SQL select statement with a reference to Amazon Comprehend, passing in data from the table. Amazon Comprehend is a natural language processing service. It uses machine learning to detect sentiment from text. Aurora will pass the call to Comprehend, and comprehend returns the results of its sentiment analysis. We do this in a batch mode, so Aurora will iteratively pass user review text to comprehend, and comprehend will return a sentiment score for each of the user feedback. So that is just a quick showcase of some of the value-added features of Amazon Aurora. I hope that was able to demonstrate why Amazon Aurora is the fastest growing service in AWS history. We have tens of thousands of AWS customers using Aurora for their relational databases. But the burning question is that if you're not already using Aurora, how do we get there? So for that, I want to jump into my demo environment. We know that migrating databases is a complex multi-phase process. And two of the fundamental steps in this process that typically require the most effort are the migration of database schemas and code objects, and the migration of the data itself. In this demo, I want to show some of the tools that can help with these steps. What I'm showing is my AWS environment. I have previously created an Amazon Aurora MySQL cluster. In fact, you can see two of them here. And this is viewing it through the AWS console. I want to call back to some of the features I mentioned earlier that you can actually explore through the console. We can add read replicas. So with add a reader, this will create an Aurora replica. This is fast database cloning so that you can create a snapshot clone without having to copy the data until the data changes. Also configuring auto scaling so that we configure the threshold and the resources needed if your workloads spike. And then the add region is doing an in-place conversion with your Aurora cluster into a global database. And then you can add secondary regions to this. These actions can also be executed through the API, so you can do these things programmatically as needed as well. These Aurora databases are MySQL compatible, so you can actually use native MySQL tools, including the MySQL Workbench. So I have a MySQL Workbench showing with connections to a native MySQL database, but I also have two connections to Aurora. So I can connect to this Aurora database using a MySQL Workbench, and we can execute some pretty common SQL. So I can create a table. We see that a table has been created. Run a insert statement. Select from that. And so we can see the row that I just inserted. And I'll drop the table. So some pretty trivial stuff, but I just wanted to show that this is, again, MySQL compatible. If you're used to writing SQL queries against MySQL, nothing really changes. So that's just to show that, again, Aurora MySQL is wire compatible with MySQL. Now, in this demo, I also have MySQL database running, and this is running in AWS, but we'll use this to represent any existing database, whether it's on-prem or self-managed on EC2, because the process is largely the same. And in the first part of our demo, I will use native MySQL client tools to back up the MySQL database using MySQL dump. And for using MySQL dump, I will go to the command line interface and we'll just run the MySQL dump command. And here, this is native MySQL dump. I am actually going to pass in the flag no data so that I can just get the schema. And so this is just pulling the schema out of MySQL database. And it goes out to the sample schema SQL file, which I can examine. And you can see that it generates a SQL script to create the schema in our target database. So I can show that source MySQL database. And the database that I pulled out was the sample database with these tables. And this is just a sample database of a company that sells and resells sports tickets, so NFL and baseball tickets, showing that the team names, the location, the ticket purchase history. And all I've done is extracted the schema. But using MySQL dump, I can also pull out all of the data in this database. So here I'm using MySQL dump again. I passed in the exact same flag, but this time I'm not passing in no data flag. And so what this would do is extract the schema and the data into this DMS sample SQL file. So I'll go ahead and run that. Here again, when I run it with the no data flag, it gives me a script with my database objects. This time it will also pull out the data. Now, this database has tables that are a few hundreds of millions of rows, so this will take some time to back up. But rather than doing that and waiting, I've actually already previously taken a backup of this database with this sample file name. And you can see that it's about 3 gigs of data. Now, in order to restore this, I can go ahead and open up another command prompt. And from what I'll actually do is log into my Aurora target. And I will show that database here, the one that I just created and dropped the table. You can see that there are currently no tables in my database. And what I would do is just use MySQL client to log into that database. I need to get my actual endpoint. So I am looking at this database, and I will use this endpoint. And here I am in just a native MySQL client. I have my sample file, so I will change my database and just issue a source command to execute the script that was generated from the MySQL dump. Now, while this script is running, I want to speak to a couple of issues I'm sure you've already noticed. The first is that MySQL dump is a logical read of your database. So for large databases, you're going to be bottlenecked by the huge I/O costs. There are certainly other tools that can perform MySQL backups more efficiently. One of the more popular tools being the Percona Extra Backup. So if you use Percona to create backups of your database, Aurora supports restoring a cluster using your data files from S3. Just to demonstrate how that works, if we go to the RDS dashboard, you can see that there is a link here for Restore Aurora DB Cluster from S3. You can click on that, or if we go to Databases, there is also a Restore from S3 button. Well, this gives you a wizard. You can select a file from S3. You provide all of the other configuration information, and Aurora will bring up a new cluster using your data files. But for the purpose of this demo, I'm just going to show native MySQL tools. I did want to call out that the Percona Extra Backup tool is a commonly used one, and so Aurora supports restoring from the data files if that's a tool you use or are planning to use. Now, the other issue I'm sure you've noticed is that this migration requires downtime from the moment you start the backup until you restore the Aurora cluster and then redirect your application. Otherwise, your new cluster won't have any of the newer data that was on your source if you continue to write to it. And so if you need to minimize downtime, AWS does provide the Database Migration Service, or DMS. And DMS is a service that can make it easier for you to migrate data from one data source to another, whether you are changing database engines or moving from the same engine to the same engine, which is what we're doing with MySQL to Aurora MySQL. DMS supports a change data capture and replication. And this is what will allow us to minimize downtime during our migration to Aurora. I'm going to go ahead and flip back and check on our restore. And it looks like it's still going. As I mentioned, we do have tables that have hundreds of millions of records, but we can actually take a look at database and see that some of the schema has actually already been applied. Hopefully just do a quick select and see that some of the data has also already been restored. So the restore is happening, but instead of waiting for the restore to complete, I've already provisioned another Aurora MySQL database, and this one has already been restored and already has the data there. So I'll use this one to demonstrate DMS. So I'll flip over and show DMS. You can get to Database Migration Service by searching for Database Migration Service, or you can actually just type DMS for short. And this will open this dashboard for DMS. Now, DMS is composed of three primary components. There's a replication instance, there are endpoints, and then there are tasks. The replication instance is the compute resource needed to move data. So to save time, I've already created a replication instance running on a C42X large, running the latest version 3.4.0. We also have endpoints, and endpoints store the information needed to connect to your source and your target databases. Here you can see that I've already created two endpoints, one for MySQL source and one for my Aurora MySQL target cluster. Endpoints also contain other configurations such as forcing SSL or TLS secure connections, or you can set session variables, for example, disabling foreign key validations at the target database if you're doing some bulk data loading. Third, we have tasks. And tasks define the actions for moving data from one endpoint to the next. Here you can see I already have a task started. The type is ongoing replication. You can see that it started and it's replicating changes from my MySQL source with the target to an Aurora MySQL cluster. Tasks can also contain other configurations such as how verbose you want your logging to be, or if you want to make some basic transformations such as renaming tables or appending suffixes to them. So as you can see, I've already provisioned a DMS replication and I've configured a change data capture task from my source to my target. I will flip back to my MySQL Workbench, which has already been connected to my MySQL database and the target Aurora database that I will be working with. So from the source, we can just do a simple count of one of my tables. We will go with the person. So here we can see the number of rows. We'll just remember the last three digits, 585. To verify, I will go into my target. And here we see the same number of rows in that same table. So we verified that the source and the target are currently the same. What I'm going to do is go to my source and I will insert a record into this table. So I will add myself as a person, just a quick count, make sure that that record is in there. We're looking for 586. So we can see that there is one new record. Now recall that DMS has a task that's already running and it is performing change data capture into my Aurora target. So I can flip over here, issue this count again, and we see that there is one row that's been added. And this is fairly trivial, but I just wanted to show that the changes happening at my source are automatically replicated to my target. I can look at my DMS task and go to table statistics, and we can look at the table person and see that two records have been inserted. This is going to show two inserts because I actually did a dry run this morning. And so there was a record inserted this morning and one record that was inserted just now live. We're replicating all of the changes from my source database to my target Aurora cluster as the changes happen. What this allows you to do is to bring your database up in Aurora using the snapshot or backup and restore process of your choice, and then use DMS to continue to replicate changes over from your source to your target so that you don't need to take your application down. And once you've done your testing and your validation, you can cut your application over to the new Aurora database. Your outage window would just be the time it takes to flush your changes from your source to your target and then redirect your application to the new endpoint. So if I were to have an application that were live, I could just change the endpoint over to my Aurora cluster, and then I can shut down the source database. And that is how I would migrate from my MySQL, whether it's self-hosted, on-prem, or on EC2, and point it to my Aurora cluster with minimal outage. Before I open the floor to questions, I also want to talk about one other scenario, and that is, what if your MySQL is already running on RDS, but you want to migrate to Aurora MySQL and take advantage of some of the Aurora storage architecture features? And so for that scenario, I'm happy to share that RDS MySQL supports Aurora read replicas. From the console, here you can see my MySQL running on RDS. You can go to action, and there is an action available called Create Aurora Read Replica. What this would do is provision a new Aurora cluster using your RDS database's data, and then it establishes an ongoing change data capture replication from RDS to Aurora. And again, once you've done your testing and validation, you can simply promote the Aurora cluster to be a primary standalone and then cut your application over. All of that is very similar to the steps that I just walked through using the backup, the restore, and then setting up change data capture. But because this is already on RDS, we just added a nice big easy button for you to just create the Aurora read replica and then do the cutover. So with that, I will yield the screen back to Alec.
Thank you very much, Locke. This was great. So the couple of questions we received was, how can I make backups in Amazon RDS?
RDS, you can configure the frequency of the backup and how long you maintain that backup up to a certain amount of time. We max out at 35 days on the automatic snapshot. It's worth noting that you can still take manual snapshots, and the manual snapshots are kept indefinitely until you explicitly remove it. It's also worth noting that with RDS, the snapshot feature is a volume snapshot. So it's not a snapshot of your individual databases. If you have multiple databases in your RDS or Aurora, the automatic snapshot will take all of the databases in that instance, not the individual databases and not the individual tables. If you want to do individual database snapshots, you could use, again, MySQL native tools like MySQL Dump or the Percona backup tool.
The other question is, what's the difference between MySQL RDS and Aurora? And what's the advantage or pros and cons between one and the other?
So from an application perspective, there really isn't any in that Aurora MySQL is wire compatible with the MySQL API. And so you have an application that is written for MySQL. You can point it at Aurora MySQL and it would run. The primary difference is under the hood, which is the distributed storage architecture. And that allows you to push the storage and log processing down to the storage layer, replicate it across multiple AZs for the durability. And we do that asynchronously. We push it down to the storage layer to make 6 replications. And if we have 4 confirmations that the storage layers have applied the changes, we confirm that the transaction was committed. And that improves the performance over MySQL and RDS, because with MySQL and RDS, we're doing the IO on disk, doing the page swap and buffer flushing. And if you want to do that with durability, high availability across multiple AZs, we have to have the standby do that synchronously. So you have to confirm the commit on your primary instance, send that change over to your standby, wait for that confirmation. And so that's kind of where the advantage is from a performance standpoint. And then all of the features that we spoke about today with the fast database cloning, being able to replicate or being able to fail over faster to any of your read replicas, auto scale, and global databases. Those are the features that Aurora will add over on top of RDS.
The other question from DBA, how Amazon RDS alleviates the work. So what they manage on behalf. Why instead of a hosting locally, I would host with RDS?
With RDS, we do a lot of the undifferentiated heavy lifting. So provisioning the server, installing the OS, the database itself, many of the configurations. So with RDS, you can kind of just go to the API, say, I want a database that is in this VPC or this availability zone or this subnet. We'll provision the hardware for you, install, configure. So that's just getting set up. And then as far as maintenance goes, automate much of the patching and upgrades for you, both at the OS and the database level. And then also maintaining high availability and the durability of your data. With a self-managed MySQL database, you would have to configure the binary log replication over to your standby. And then if your primary were to go down, you would have to switch over to your standby. Whereas with RDS, you can just, or at least with Aurora, you can point at the endpoint and what redirects you to the standby automatically for you. At least with Aurora, even if you don't have a replica to fail over to, best effort to replace your primary and bring it back up, restore the data. And so the downtime there without any manual intervention is about the time it takes to bring a new instance back up.
The other question is it possible to use Aurora for big data?
There's a lot of different use cases where we can use Aurora. As I mentioned, we scale up to 64 terabytes with Aurora. You can scale up your reads. So if you need to scale, add more compute, add more storage, we can get fairly large with Aurora just as a relational database. Now, there are other use cases where if you're churning through the data, performing some pretty complex aggregations and calculations, Aurora does integrate very nicely with other AWS services, including S3, including Redshift. And in fact, Redshift has federated queries so that if you were to host or conform many of your data sources into a data warehouse on Redshift, you can actually have an external query executed on Redshift that reaches into Aurora and pull some of that data so that you can join data from Aurora to your Redshift side by side. Aurora also supports importing and exporting to S3. That allows you to use services like AWS Glue or Amazon Athena to churn through your data in S3.
So is it possible to use Aurora as a backend for a Drupal CMS website that lives on a local server?
Yes, all you really need is the connectivity from your local server to an Aurora database. Aurora lives inside your VPC, and so within your VPC, you control what connections are allowed in and out and within your VPC using security groups. And so you could hypothetically open up your Aurora database to the public internet, although that's not recommended, but you could say funnel it down to your specific IP addresses, and so that only your server can talk to, or your data center can connect to the database. And in addition to that, we can also set up network forwarding so that the VPC is kind of extending your on-prem data center, and so that you can have private connections between your data center and your VPC.
So I'd like to thank everybody and see you guys in the next office hours on the September 24th. Luck again. Thank you very much. Bye.
Thanks, everybody.